Welcome to the first episode of Chem Talks, where chemical reactions happen. So, myself Samir Tasildar.
And my name is Vedant Tambe, and today we are going to discuss about some hot, cool and kinda nerdy topic. No, it's not something about new Netflix movie.
Then, Mr. Tambe, what is the topic about?
It's about Chilton-Coleman analogy and Reynolds analogy.
Okay. So, if you have ever sat in class thinking that why every subject in chemical engineering feels like deja vu, then well, thanks to Chilton and Coolburn, because they have established relations between heat, mass and momentum transfer, which are our holy trinity, and gave more alike relationships than they are actually.
Exactly, he is right. So, before moving forward, I must ask you one question. Have you seen Avengers movie? Have you?
Yes,
I
definitely.
bet my audience has also seen the movie. So, this topic is nothing but Avengers of transport phenomena, where heat transfer is Iron Man, mass transfer is Captain America, and momentum transfer is our beloved Thor. Different powers, but somehow they follow the same rules.
Yes. So now let's move further. Do you know what is the best part about this analogy?
What?
This analogy makes our life a bit easier. You don't need to remember separate correlationships for heat transfer, mass transfer, momentum transfer. You just tweak a few variables and boom, you have solved all your problems.
Cool, isn't it?
Yes. So, Mr. Tambe, one
Yes.
thing that always comes into my mind is whenever I study Chilton-Coolburn analogy, I always think, did they work together?
No, they didn't publish their work together.
Yes.
This analogy is named after them because someone else combined their separate contributions and published it. It's like a nerdy arranged marriage.
So today we are gonna break this topic into simple terms. That is, Chilton-Coolburn analogy will study in depth how it relates J factors, why it works, and how it is used in different problems. We will also solve few problems related to it, and various assumptions, correlations, everything in detail will be studied further in this video. So, after covering all the basic points related to Chilton-Coolburn analogy and Reynolds analogy, let's dive into the deep understanding of the OG topic, that is the Reynolds analogy. So I request Mr. Tambe to explain few concepts from basics to advanced, the assumptions, the limitations and mathematical expressions that are involved in the Reynolds analogy.
Okay. So, Reynolds analogy is nothing but it's a shortcut. In smart way, it relates the different types of transfer coefficients such as heat, mass and momentum. If you don't mind, can I dive into some history?
Yeah, sure.
Okay. So, in 19th century, Osborne Reynolds noticed that the equations describing the momentum transfer and heat transfer looked a lot similar, especially when the flow is turbulent.
Okay.
So, he thought, why not create a connection? He created a connection, and later on that connection became known as Reynolds analogy.
Oh, so that was the story behind it.
Yes.
Okay.
So, originally, the original idea behind this was if the fluid is transferring momentum, it's likely also transferring the heat.
Okay. So, can you give me a mathematical expression related to it?
Yes. So, the mathematical equation behind this Reynolds analogy is that Stanton number equals the friction factor by 2. This equation tells us that if we know how much momentum the fluid is experiencing, then we can estimate how much amount of heat it is experiencing without even solving the different equation for heat flow.
Okay.
Okay. So now before solving any questions, keep these two assumptions in your mind. And these two assumptions are, first one, it is only applicable, the Reynolds analogy is only applicable when the flow is turbulent, and second, when the Prandtl number is equal to 1. So, for most of the gases, we can use Reynolds analogy, but not for most of the liquids. We need to keep in mind that Prandtl number is equal to 1 and the flow is turbulent.
Okay. So, thank you for explaining the topic so nicely. So now you might have got a deep understanding about what is Reynolds analogy, what are its assumptions, what are its limitations. So now we will also solve some problems related to Reynolds analogy. But further, let's move into next topic.
So now we will be diving into something really core to chemical engineering, that is Chilton-Coleman analogy. So Mr. Tasildar, can you explain me?
Yes, this one is a must known if you are dealing. Sorry.
Restart. Restart.
This one is must known if you are dealing with. This one is must known if you are dealing with.
So now we will be diving into something really core to chemical engineering, that is Chilton-Coleman analogy. Mr. Daskar?
Yes, this one is must known if you are dealing with heat exchangers, mass transfer, and even if you are designing reactors. So let's break it down from basic. Now,
So can you explain me what is Chilton-Coleman analogy?
okay. So as Mr. Tambe has given us advice, let's start from the basic definition. So the definition of Chilton-Coleman analogy is that it is an empirical analogy that connects momentum transfer, mass transfer, and heat transfer. Okay. Now think it as a bridge. If you know fluid flow and all the frictions involved, you can easily estimate the rate of heat and mass transfer. So this is the basic definition and a clear idea of what is Chilton-Coleman analogy.
Okay. So there are some J factors in this analogy or something?
Yes.
Can you explain me that?
Now this analogy uses J factors.
Okay.
J factors are nothing but they are dimensionless numbers that connect various heat transfer and mass transfer coefficients. Jh is given for mass and heat transfer and Jm is given for mass transfer. So they are related to friction factor.
Okay. So can you explain me the key formula or tell me the key formula?
Yes, definitely. They are related to each other by a formula where the formula involves JH, JM and F. So the formula is JH is equals to JM is equals to F by 2, where F is the friction factor and other two terms you are already familiar with. So this is the overall idea of the J factors and the key formula.
So moving forward, my next question is where can we restart? So moving forward, my next question is where can we apply this analogy?
Okay, so we can apply this mostly in turbulent flows, inside pipes, flow over flat plates, and inside the duct systems. You know, this analogy is super useful in heat exchangers, cooling systems, and absorption towers. Now, as you are all now familiar with the J factors, we related J factors for heat and mass transfer with the friction factor, and the formula was JH is equals to JM is equals to F by 2. But now we introduce specific formula for JH and JM.
Okay.
You know, for JH we can make it into dimensionless numbers, where JH can be written as Prandtl number to the power 2 by 3 into Stanton number for heat transfer. Similarly, we can write for mass transfer as Jm is equals to Stanton number for mass transfer into SC to the power 2 by 3.
Okay, so here is an interesting term of 2 by 3.
Yes.
So can you explain me about something about why the term is 2 by 3 and not 3 by 2 or something 1 or else?
Very nice question. So this comes from a boundary layer theory. Basically, what happens is in turbulent flow, the thickness at concentration layer increases at different rates.
Okay.
So this 2 by 3 experimentally fits. So this doesn't mean it's just about the theory, but it's also about the practical knowledge.
Okay, very nice. So, as we have seen the most of these mathematical equations, now we are going to see what are the limitations. So, can you explain me what are the limitations?
Yes. Now you know what are the limitations for Reynolds analogy. Same, we have limitations for Chilton-Coleman analogy as well. So it struggles with different areas. First of all, it struggles with laminar flow. It doesn't really apply to laminar flow regions.
Okay.
Then it also struggles for rough surfaces. As we have seen all the equations, they are for smooth surfaces. But for rough surfaces, there are some errors.
Okay.
Next, it also struggles with convection or radiation. It doesn't work well. Then for high viscosity fluids also it doesn't go that well. So
Okay.
these are the basically limitations ahead for Chilton-Coleman analogy.
So, we have seen the limitations. Now, can you wrap up and tell me the summary of Chilton-Coleman analogy?
Yes. So first of all, we went through what is Chilton-Coleman analogy, its background. We have looked into the definition, its relation. We have looked into J factors. We have related it to heat transfer, mass transfer, and equated with the friction factor. Also, we looked into specific formula for JH and JM. Also, you asked a very good question about the power 2 by 3. So that's also you have understood. We looked into limitations and everything is now crystal clear about Chiltern-Coolbert analogy.
Okay, so from now onwards, we are going to solve some derivations and some numericals on this topic. So let's move forward. So now let us start the numerical part and the derivation part. Firstly, we are going to solve the problem which says derive both generalized analogy equations, that is Reynolds analogy and Chiltern-Coolbert analogy, starting with explaining physical interpretation of all three transfer coefficients. Give the limitations of both Reynolds analogy and Chiltern-Coolbert analogy. So this is the question and we are going to see its solution. Now, before deriving the Reynolds analogy and Chiltern-Coolbert analogy, we are going to see the physical interpretations of the three transfer coefficients. Firstly, we will see the physical interpretation of the friction factor. Now, let us assume there is a flat plate which is suspended in a fluid whose velocity is v infinity. Let the plate be stationary and length of the plate be L, whereas its width be W. This is y direction and this is x direction, and the wind is moving in x direction, positive x direction basically. So in order to calculate the total momentum flux at the wall, that is at the surface, we are going to calculate the momentum flux we are going to calculate the molecular flux plus convective flux at the wall, that is at the surface of the wall, that is at y is equal to 0. So the total momentum flux pi xy at y is equal to 0 is given as molecular flux plus convective flux. Now, so in order to calculate the convective flux, we want a density into Vx into Vy. Basically, the Vx will be 0 because the plate is stationary and the fluid which is in contact with this plate at y is equal to 0 will be stagnant, that is no slip boundary condition. So Vx and Vy both will be 0 and this term will be 0. So this momentum flux will be given as pi xy is equal to tau xy at y is equal to 0, that is only molecular flux, which is equal to tau is equal to mu dvx upon dy using Newton's law of viscosity. This is our equation 1. Also, we have one equation which is given as tau is equal to half rho v infinity square f. This is nothing but in order to calculate the molecular flux, because we need the value of molecular flux and it cannot be calculated directly. So we introduce the dimensionless term F, which is friction factor. Now, combining these two equations, we get half F is equal to mu by rho in v infinity square dou Vx upon dou y at y is equal to 0. Now, in order to calculate the dou Vx upon dou y, we are assuming the constant velocity gradient throughout. So this is actual velocity distribution and we are assuming it is ideal, that is v infinity divided by delta. So dou Vx upon dou y at y is equal to 0 becomes v infinity by delta. This is our equation 4. Now substituting equation 4, that is this, in the equation 3 and multiplying by characteristic length, we get half f into half f Re is equal to LCH by delta. This indicates the product of F, that is friction factor, with Reynolds number is directly proportional to the characteristic length and inversely proportional to the thickness of the boundary layer. This also gives the Reynolds number, which is equal to LCH v infinity into rho by mu, which is viscosity. This is nothing but the physical interpretation of the friction factor. So, as of now, we have seen the physical interpretation of friction factor in the previous case. Now we are going to see physical interpretation of mass transfer coefficient. So, let us consider a flat plate suspended in a uniform stream of fluid of species B, having velocity v infinity and species A concentration as Ca infinity as shown here. The surface of the plate is also coated with the species A with concentration Caw. Let the length of this plate be L and its width be W. Now, as of engineers, we are interested in total number of moles of species A transferred from the plate to the flowing stream. This can be calculated by integrating the total molar flux at the wall over the surface area. The total molar flux is given as NAY at y is equal to 0 is equal to J star A at y is equal to 0 plus CA V star y at y is equal to 0. This is nothing but the molecular molar flux, and this is nothing but the convective molar flux. For low mass transfer, this case can be written as NAY at y is equal to 0 is equal to NAW, which is equal to J star AY at y is equal to 0 equals minus DAB dou CA by dou y at y is equal to 0. This is nothing but our equation 1. Also, there is another equation relating the molar flux and the mass transfer coefficient, which is given as NAW is equal to Kc CAW minus CA infinity. This is nothing but our equation 2. Now, combining 1 and 2, we get Kc is equal to minus DAB CAW minus CA infinity dou CA by dou y at y is equal to 0. This is nothing but our equation 3. The convection mass transfer coefficient can be determined from this equation if the diffusion coefficient, overall concentration difference and the concentration gradient at the wall are known. Since calculation of the concentration gradient at this wall or at the surface of this plate is little bit difficult because the concentration distribution curve is somewhat exponentially increasing. So we idealize this case as this, and it is given as dou CA by dou y at y is equal to 0 equals CA infinity minus CAW divided by delta C, assuming constant concentration gradient. This is nothing but our equation 4. Now, combining equation 3 and equation 4, we get AC is equal to DAB by delta C. This indicates that mass transfer coefficient is directly proportional to the diffusion coefficient and inversely proportional to the concentration boundary layer. So, as we have seen physical interpretation of friction factor and mass transfer coefficient, now we are going to see the physical interpretation of heat transfer coefficient. So, as we considered the plate in our two cases, here also we are going to consider a flat plate suspended in a uniform stream of fluid having velocity V infinity and the temperature T infinity. The temperature at the surface of the plate is kept constant at Tw. So, as engineers, we are interested in total rate of heat transfer from the plate to the flowing stream. This can be calculated by integrating the total energy flux at the wall over the surface area. So, total energy flux is given as Ey at y is equal to 0 is equal to Qy at y is equal to 0 plus rho Cp T By at y is equal to 0. This is nothing but the molecular energy flux at the wall, and this is convective energy flux at the wall. As a result of no slip boundary condition at the wall, the fluid which is in contact with the plate is stagnant, and heat is transferred by the pure conduction through the fluid layer immediately adjacent to the plate. Therefore, this equation reduces to Ey for y is equal to 0 is equal to Qy, y is equal to 0 is equal to Qw is equal to minus K dou T by dou y as y is equal to 0. So this term is cancelled. Now, also there is another term relating the total energy flux, which is given as Qw is equal to H Tw minus T infinity. This is nothing but relation between the energy flux and the heat transfer coefficient. This is our equation 2. Now, combining equation 1 and equation 2, we get H is equal to minus K divided by Tw minus T infinity into dou T by dou y at y is equal to 0. This is nothing but our equation 3. The convection heat transfer coefficient can be determined from this equation if the thermal conductivity K of the fluid, overall temperature difference, the temperature gradient at the wall are known. Since the calculation of the temperature gradient at the wall requires the temperature distribution in the fluid phase to be known, the actual case is idealized as shown here. So, the entire energy resistance to the heat transfer is assumed to be due to the stagnant film in the fluid next to the wall. The thickness of the film dt is such that it provides the same resistance to the heat transfer as the resistance that exists for the actual convection process. The temperature gradient in the film is constant and is equal to dou T by dou Y at Y is equal to 0 is equal to T infinity minus TW by dou T. This is nothing but our equation 4. Now, by combining equation 3 and equation 4, we get H is equal to K by dou T. This indicates the thickness of the film dou T and the value H. So basically this equation indicates that heat transfer coefficient is directly proportional to the thermal conductivity and inversely proportional to the thickness.